All right, section 2. This section is entitled substitution. And so what we want to do is we want to figure out numbers that work for both, right? Numbers that work for the top and the bottom. You should be able to see numbers that work for the top automatically, like 5 and 0 or 0 and 10, right? But the question is, will they work for the bottom, right? Those pairs of numbers that work for the top don't work for the bottom. So how do we find the ones that do? Well, there's this method we've talked about called substitution. And what we want to do is we want to take one of our equations. I'll have this be the blue equation. And what we're going to do is take one of these equations and we're going to get x or y in terms of the other variable. So that technique we talked about in section 1, right? Get x in terms of y or y in terms of x. If I were to get x on its own here in the blue equation, I'd have to subtract the y to make it 0 and divide by 2. So everything's divided by 2. That's fine. Here I would have to add 4y to make that 0 and then divide by 3. So everything's divided by 3. Here to get y on its own, in the bottom equation, I'd have to subtract 3 x's to make it go away and then divide by -4. But this is the one I'm actually going to get on its own, that y value. And it's because the only thing I need to do to get it on its own is just subtract 2x. So now y is on its own. So that's the easiest for me to get on its own. So that's what I'm going to do. I'm going to take that equation, 2x plus y equals 10. And I'm going to subtract 2x to make this 0. And I'll do it to both sides to make sure the equation's balanced. And what we end up with is 0 plus y, that's why I did it, so I get y on its own, equals 10 minus 2x. And while this doesn't answer our question of what numbers work for both, it does put y into this perspective, right? We know y in terms of x now. And why that is useful is because we're going to take this junk right here, right? That's what y equals. And we're going to plug it into the other equation for y. So instead of thinking of this as -4y, we're going to think of it as -4 times this. And why that's useful is because when there's two variables, we have infinite answers, right? There's lots of numbers that make this work. But when we replace y with x, then we only have one variable, x and x. And you'll see that in a second. So we have 3x minus 4, and instead of y, I'm going to plug that stuff in, like I said. So what am I plugging in? Well, instead of y, I'm going to have 10 minus 2x. And whenever you plug something in, always wrap it in parentheses. And so now you'll notice that we have kind of a long equation, but it's only one variable. We don't have two variables anymore. We just have x's. We don't have x's and y's. So now, if I get my x's together, I'll be able to find out the x that works for both, right? It's kind of like these two equations got combined. So now I'm finding the x that works for the blue and the red. So we'll call it a purple equation. So in order to get my x's together, I first have to distribute that -4. I could, if I want, divide everything by -4 to get rid of that. But of course, these aren't divisible by that, so I won't. So when I distribute that -4 and I times it to 10, I get -40. And when I distribute that -4 to this other term, I get a positive 8x's. Because again, it's -4 times -2x. That's positive 8x's. And we're going to get our x's together. They're on the same side already, so I don't need to use any properties of equality. This just says 3x add 8x, so I get 11 x's, and I still need to minus 40. And at this point, you could continue using properties of equality to get x completely on its own and solve for x, but I'm just going to use my brain, because the whole reason of getting x together in one spot is because here it's kind of hard to figure out what number you need to plug in to make it all work, right? But here it's actually pretty easy. So go with me for a second and let's use our brains. Since x is all in one spot, I can cover it up and think, what minus 40 is 37? Well, if it was 40 minus 40, I get 0, right? And 41 minus 40 gets me 1. So it's got to be bigger than 40. In fact, it's got to be 37 bigger than 40, doesn't it? It's got to be 77 minus 40 gets me 37. So I need this to be 77. So what times 11 gets 77? Well, 7. Our answer is 7. If you don't see that, hopefully you see what we just said, that this had to be 77, right? So I'm writing that down. This part has to be 77. You could also get that by simply adding 40 to both sides. A little property of equality, right? These become 0, and you get this. Now from here, hopefully you can see that 7 times 11 gets you 77. Because if not, even if you divide everything by 11, like a lot of people tell you to, you still have to know what 77 divided by 11 is, right? You still have to be able to simplify this. And if you know that it's 7, then you probably could have figured that out up above, right? So x is 7. So this is what we call substitution. Taking something like this and subbing it in for another variable. What that does is get us one equation with one variable, and we can solve for one of the variables. So we know that x is 7. Now we need to figure out our y value that pairs up with it, that works for both. You could plug in 7 here and solve, or you could even plug it in here and get y, right? Any of those will work because, again, 7 should work for both of them. And so let's do it in all three. So if I plug in 7 here, I get 14. 14 plus what gets you 10? Well, 14 plus negative 4 does, right? So hopefully these both work for this one. 21 plus 16, that's 37. So totally works for both. Just to be clear, you could have also plugged 7 in here. 10 minus 14 is negative 4. So here are the numbers that work for both. In fact, it's the only pair of numbers that work for both. Because if you think of it, these are linear equations. So we have a line, and then we have some other line. And these lines represent all the pairs of numbers that work. So all of these dots represent numbers that work for the red equation. All of these dots on this line represent numbers that work for the blue equation. And it's easy to find numbers that work for one of them, right? Like 5 and 0 for this, or 0 and 10, right? But the only pair of numbers that works for both will be where they intersect, and that's this right here, 7, negative 4. It's the only pair of numbers that works. The only other way we could get it to intersect multiple times is if they weren't linear equations, right? If one of them was curvy, it could hit twice, right? So if it has a solution, it's only going to have one pair that works, which is why guessing and checking isn't the way to go, right? What you really want to do is use this method called substitution, where you switch stuff out so you can find the one answer that works. Cool. So what do? We got x in terms of y, or y in terms of x. In this case, we got y in terms of x, and we plugged it in using sub, right? Substitution. Then we solved. Once we knew one, we got the other for free. We're going to do that same thing for part D, because a lot of people have questions about this, right? Same idea. I want numbers that work for both, but these are messy equations. So the first thing I'm going to do is I'm going to clean up these equations. So this equation right here, if I get all my x's and y's together to make it all nice and neat, if I add 0.2x to both sides, that'll make this gone. And now I'll have 2.2x's. If I also subtract 0.1y from both sides, that makes this go away. And if I subtract 0.1, I get negative 3.1y, right? I'm already subtracting 3. If I subtract another 0.1, I'm subtracting 3.1. And that's going to equal negative 3.2. That still looks pretty bad, but it's better than what I had. Now, if I add y to both sides for this bottom equation, then I'll get rid of this, right? I'll make it 0. Adding y to negative y makes 0. So I've got a positive y on this side now. And if I subtract 0.6x from this and that, that'll go away, and I'll get 0.4 x's. Make sure I don't lose those decimal points. And of course, what's left over will just be equals. This equal sign, here's the right side of the equation, 8.8. Don't lose those equal signs. So this looks a little bit better to work with, but still kind of awful, right? So I think what we need to do is we need to get rid of these decimals. That's what I think we should do. You could, if you wanted, subtract this over, get y on its own. That's pretty nice, and then plug it in. But I think I'm going to get rid of the decimals. And the way I'm going to do that is I'm actually going to times everything by 10. So if I times this by 10, and this by 10, and this by 10, it won't change the problem. It'll just make it look different. And I'm going to call it the green equation. So this is my green equation. When I times by 10, 2.2 is the same thing as 22 over 10. So of course, timesing by 10 just gives you 22. Or in other words, moves the decimal place over 1. So timesing by 10 turns that to 22x. Timesing by 10 makes that negative 31y. And timesing that by 10 makes it negative 32. And so the numbers are bigger, but at least they're not fractions. Let's zoom in a little. Cool. So that's what I did. I took this and I times everything by 10. The bottom equation, I think I'll make orange. And I'm going to times it by 10 as well. It just so happens that 10 is the number I want to use. For both, since I need to move the decimal place over twice, the numbers could have been different between the top and the bottom equation, right? So this is going to give me 4x's plus 10y's equals 88. And you might notice that this bottom equation, I could divide by 2 to make it simpler, right? So I actually didn't need to times by 10. I needed to, if I times by 5, it would have worked. But no big deal. I'll just divide everything by 2 now. And that'll make our new equation 2x plus 5y equals 44. So I'm going to write this nice and neat now. 22x minus 31y equals negative 32. And our other equation, after we simplify, is 2x plus 5y equals 44. Now, before we start, we should always ask ourselves, are these actually two different equations, right? We saw here that we can change 4x plus 10y equals 88 into this, and it doesn't change the problem, right? So if there was a way where I could multiply to make this match that, then they would be the same equation, and we'd be the same line, right? And they would share all their solutions, so there'd be infinite solutions. So if I times this by 11, it does match. But if I times everything by 11, like I have to not change the problem, that becomes 22, awesome, but this becomes 55, not negative 31y. So we know these are different equations. That means the scenario we're looking at must be something like this, where they intersect at one random spot, and that's the random spot we're looking for. So now we're going to do substitution. So in this case, I think what I'll do is I will get x on its own, and here's why. Not just because 2 is the smallest number, but when I get x on its own in the bottom equation, I'm going to subtract that over, and I'm going to divide by 2, right? So I'm going to get x equals something divided by 2. And when I plug that in for x, this is divisible by 2. So my math will kind of work out kind of nicely for me there, right? My calculations. So I'm going to show you what I mean by that. So if I take this bottom equation, and I'm going to do it in my head. I originally had 44 on the right side. If I subtract that over, I get negative 5y. So that's gone, and I subtracted it over. And if I divide by 2, I get regular x. So I divide everything by 2. So what I'm going to do is I'm going to take this, and I'm going to sub it into x in the other equation. And notice what will happen, right? I'll take 22, and I'll times it by all this, but I'll also be dividing by 2. That divide out to 11. That'll make my life a little bit easier. So just to recap, first we clean up the problem, and that's what makes things hard. Makes this problem hard, right? There's stuff everywhere. We need to get rid of decimals, right? It's kind of a pain. But after we have this, it's not going to be too bad. So let me rewrite this. This equation is 22 times whatever x is minus 31y equals negative 32. And instead of writing x, we're going to substitute this, because that's what x is in terms of y. And now we only have one variable. It's just y values. So I'm going to move this up here so we can see it, right? Just y values. And again, the reason I like that divide by 2 there is because instead of timesing the 22 into everything, I can divide by 2 first. So this divides out to just 1 over 1. 22 divided by 2 is just, 11 over 1. There we go. It's just 11 over 1. So now when I distribute into here, I'm not timesing everything by 22, I'm only timesing by 11. So 10 times 44 is 440, and then 1 times 44 is 44. If I put those together, I get 484, right? 11 44s is 484. And 11 negative 5s is negative 55. Why? So at this point, it's just Chapter 4 stuff, getting our variables all together. 484. This is on the same side, so we're going to get 86y's negative. And I'm going to rearrange this to make it nicer. So I'm going to add 32 to this side. When I do that, it'll end in a 6, and it'll be 516. And if I add that to this side, I get 86y. Now, if we had to guess what value y would be, what times 86 gets 516? Well, I know it ends in a 6. So what times 6 ends in a 6? Well, if I times it by 2, it'll end in a 2, because 6 times 2 is 12. 3 times 6 is 18. That'll get to end in an 8. 4 times 6 is 24. That'll get to end in a 4. 5 times 6 will end in a 0 because it's 30. 6 times 6 will get me a 6 in the end because 6 times 6 is 36. So I know my answer has to end in a 6. And if I want to get close to 500, I think 46 is a good answer because 40 times 80 will get us 480. That's pretty close to this, right? So 56 is probably too big, 36 is probably too small. So I'm going to guess 46. Let's check and see if that's true. Is 86 times 46 516? Well, if it is, then 86 times 40 plus 86 times 6 should get us 516, right? That's 46, 86. So looks like I've got 40 times 86. Well, we know 4 times 8 is going to get us 32. So 40 times 80 is going to get us 3200. And 40 times 6, well, 4 times 6 is 24. So 40 times 6 is 240. And then, of course, here, 6 times 80 is going to get us 480. And 6 times 6 is going to get us 36. So if we add all these up, looks like we're going to get 3680 and 276. Looks like we're going to get a total of, oh, hold on a second, 40 times 80. So 4 times 8 is 32 with 2 zeros on the end. Oh, no. Perhaps our answer is far too big, right? This is gigantic. 3,000 and something. It's way more than 516. So where did I go wrong? Oh, I know where I went wrong. It definitely ends in a 6 because it is 6. 6 times 86. Let's check that. I was thinking 5,000 something. So if we do 80 times 6, it's 480. And 8 times 6 is 36. And of course, that will add to 516. So there it is. Right. So our answer for y will be 6. So the number that makes both equations true for y is 6. So if we go back to our problem over here, here are our two equations down here. Right there, I'll cover up this stuff. So here are our two equations. Apparently the y value is 6. So in other words, I can write it like this as a grouped pair, an ordered pair. Now I could plug the 6 in here, or I could plug it in there to solve, or I could plug it in here down at the bottom and get x for free. It's really up to you. Should work in all of them though. I'm actually going to plug it in here because it'll make my life easy. So when I plug in 6 here, I get 40 minus 30, which is 14. 14 divided by 2 is 7. Now we should check these. Does 7 and 6 work for these problems? Looks like 140 plus 14, so that's 154. And we're taking away 186. So yes, that will get us negative 32. Here, we get 14 plus 30. Yeah, that's definitely 44. Here's our answer to both. So quite a doozy. This is probably the worst case scenario. It's super messy. Multiplying to get rid of decimals, right? Quite a bit of work. The main lesson here, I think, is that simplification and then choosing which one to get on its own. I wanted the one that would divide by 2, so it divides out nicely with that 22. So that's 521. Let's take a look at 523. I have some good news. This one is more complex, which means it's actually quicker to solve. So we have two equations, a red one and a blue one. We want to find numbers that work for both. Now, before we get going on this, we should ask ourselves, is this a situation where we have two different lines and they intersect at some point and we need to go find it? Or is it that they're the same equation so that when we look at answers that work for one and answers that work for the other, they'll be the same thing, right? Anything that works for one will work for both. Or is it possible that they're very similar, so similar that they never actually intersect, and there'll be no solutions? Well, if you look at this, I can simply times the top equation all by 3, and it will match up perfectly. Which means, since this is 15x, that's negative 18y, and that's 3, they're the same equation. Means anything that works for one will work for the next. So if we want to find some answers that work for this, we can find lots of possible answers. Let's find 3 of them. So here, let's just use the original equation here, the red one, the top one. Multiples of 5, multiples of 6 are separated by 1. Well, what if I did 1 for this and made that 5, and I put a negative 1 here to make that a positive 6? Ooh, let's do this, yeah. So make that a positive 6 and this a minus 5. 6 minus 5 is 1. So we found our first solution. And then if we use what we learned from earlier in section 1, this is our delta x right here. We just got to change the sign. So it's sort of delta x. And this is our delta y. We can find some answers really quick. So delta x is actually plus 6. And delta y is actually plus 5. And using that, we should be able to find lots more answers. If we add 6 to that, we get 5. If we add 5 to that, we get 4. Let's check it. 25 minus 24 is 1. Perfect. If we do that again, we get 11 and 9. 55 minus 54 is 1. And of course, these will work in the bottom because the bottom's the same thing as the top. So there were infinite solutions here. And here are some examples that could work. Okay, so that's 5, 2, 3. I believe there's one more. Yes, 5, 2, 4. And this one I believe had a star next to it. I could be wrong. And that's because this one looks really challenging, right? The numbers look awful. We're going to have to do substitution. We're going to have to divide by 12 or 91 or 92 or 13 to get something on its own. That seems really terrible. But here's the big brain play. If they both equal 273, then they equal each other. So here's equation 1. 13p minus 92q. And it equals 273. But apparently so does equation 2, our blue equation. It also equals 273. So if they both equal 273, then they equal each other. And if we just rearrange this equation to get an equation where our p's and q's are all together, we subtract 12p from both sides, we just get p. If we add 91q's to this, we get minus 1q. So we know that this is true. P minus q is 0. Of course, what does that mean? That means p is whatever q is. So we can rewrite this problem. Every p we can replace with a q or vice versa. And that's going to make our math really easy. This is actually a single variable problem, because p and q are the same thing. So when we do this, we can get our p's together right away. And if we get p, we get q because they're the same. So 13 minus 92. Well, 13 minus 2 is 11, right? So I can rewrite that as 11p minus 90p equals 273. And then if I subtract 90 from this, well, subtracting 90 from 10 gets me negative 80, but I got to put 1 back. So it looks like negative 79p equals 273. And while our answer is going to be gross, what do you times by negative 79 to get 273? It's this abomination. We do know it's the same thing as q. So there are both our answers. Negative 273 over 79, comma 273 over 79. Both of them negative. Problem solved. All right, so that's it for section 2, and that's it for now.